Hi everyone. In the last lecture, we have discussed about the spectral mapping theorem for normal operators. The polynomial version we have seen. That means if P is a polynomial of two variables, z and z bar, and if T is a normal operator, we have shown that spectrum of P T star equal to P of lambda lambda bar, where lambda is in the spectrum of T. Now we ask the question, can we extend this result to continuous function? That means if you have a continuous function defined on the spectrum of T, can we say that spectrum of f of t equal to f of spectrum of T? This is the question we are going to address today. So this we have already discussed for self-adjoint operators earlier. So today we are going to discuss the following result. Let T be a bounded normal operator and f is a continuous function defined on the spectrum of T and taking values in C, that is f is from spectrum of T to C, which is continuous. Then we can show that spectrum of f of T is f of spectrum of T. This is nothing but set of all f lambda, where lambda is coming from the spectrum of T. So this is known as spectral mapping theorem for normal operators. Okay, so let us look at the proof of this result. In the self-adjoint case, what we have done was, if T is a self-adjoint operator and f is a continuous function defined on the spectrum of T, then we approximated f by sequence of polynomials with respect to supremum norm, and f of T we defined as the limit of the polynomials of T. Now we are going to do the same here also, but here we have to look at polynomials in two variables. So before discussing this result, let us look at how to define continuous function of an operator. So let us take T to be normal. We know how to define P of T star. So if we have P of z bar, we have a polynomial, or we can take a polynomial in two variables x y as summation a n m x power n y power m n m equal to 0 to k, where a n m is a complex number and x and y are also complex numbers. Okay. Then P of T star is nothing but summation nm equal to 0 to k a n m t power n t star power m. So this is the operator which is defined as P of T star. Now we want to define what is f of T. So let us take a continuous function from spectrum of T into C. Then by the Weierstrass theorem we can approximate this f by sequence of polynomials in the uniform norm. Here polynomials in two variables. Let Pn be a sequence of polynomials in two variables such that Pn converges to f in the uniform norm. So then we define, as in the case of self-adjoint operator, f of T we define as limit n tends to infinity Pn of t t star. When t is self-adjoint, we have defined this as limit of Pn t only, because t equal to t star in that case. So here we get two operators t and t star. First of all, we have to show that this operator is well defined, in the sense that if there is another sequence of polynomials Qn, if Qn is a sequence of another polynomials approximates f of z uniformly, then we want to show that Qn of t t star also converges to f of t. If you look at norm of Qn of t t star minus Pn of t t star, we can show that this is less than or equal to sup norm of Qn minus Pn for every n in n. This can be done easily, because we can easily show that P of t t star norm of this less than or equal to sup norm of P. So from this we can conclude. Now if you want to look at norm of f of t minus Qn t t star by triangle inequality, this is less than or equals to f of t minus Pn of t t star plus norm of Pn t t star minus Qn of t t star. Now the first one goes to 0, so this is anyway less than or equal to f of t minus Pn t t star, and this is nothing but norm of Pn minus Qn sup norm. We know that norm of Pn minus Qn goes to 0, and so we can conclude that this goes to 0 as n tends to infinity. So from this we can conclude that f of t is well defined. Let us recall about the Gelfand map. If A is a commutative unital C star algebra, and MA is set of all functional from A into C, phi is linear, multiplicative, and norm of phi less than or equal to 1. Of course, we can show that norm is less than or equal to 1 all the time. So non-zero, you have to assume that f is non-zero, phi is non-zero, linear multiplicative map with this property. This is a maximum ideal space of A. So the Gelfand transform is from A to C of MA. We know that MA is weak star compact. So here A is mapped to gamma of A. Gamma of A is a map from MA into C. It is a continuous function from takes phi of phi into phi of A. Okay. So when we have a commutative unital C star algebra, then gamma preserves all the C star algebra properties, namely gamma is linear, multiplicative, gamma preserves the involution, and gamma is an isometry, and gamma is onto. So in particular, in our case, if you look at, let us take T to be normal. Let us take A to be the C star algebra generated by I T T star. So this is a commutative unital C star algebra. Now we can look at the Gelfand map from A into C of MA. So as I told earlier, this is linear, gamma is linear multiplicative, it preserves the adjoint or involution gamma A bar for every A in A. It's an isometry. Gamma A is nothing but norm of A. This is subnorm. Gamma is onto. Okay. So gamma of P T T star at lambda is P of lambda lambda bar for every lambda in the spectrum of T. This can be proved easily, and if S is a bounded operator such that S commutes both T and T star, then we can show that S commutes with every element from A. SA equal to AS for every A in A. Okay. So this is a continuous functional calculus for a normal operator, and in fact T's identity is mapped to identity. Identity is mapped to identity in C of MA, that is a constant function 1. Now we want to prove the spectral mapping theorem. Spectrum of f of t equal to f of spectrum of t. This we want to show. Let us take lambda in the spectrum of t. Then we know that we want to show that f lambda is in spectrum of f of t. So let us approximate. Let Pn be a sequence of polynomials such that Pn of lambda lambda bar maps to f of lambda. Pn of lambda lambda bar converges to f of lambda for every lambda in the spectrum of t. So we can write this as Z. Okay. Now if you look at, then we have f of t minus f lambda I. This is limit tends to infinity. Pn of t star minus Pn of lambda lambda bar identity. Okay. Now since lambda is in the spectrum of t, so by the earlier spectral mapping theorem which we have proved for polynomials, so this is in spectrum of Pn of lambda, Pn of T star. But this we know that Pn of spectrum of T. Okay, that means this Pn lambda bar is in the spectrum of T star. So this is the right hand side. This is not invertible. Hence we can say that left hand side is also not invertible. Because set of all non-invertible elements forms a closed set. So from this we can actually conclude that therefore f lambda is in spectrum of f of t. So we have taken lambda from the spectrum of t and we have shown that f lambda is in the spectrum of f of t. So we have shown that f of spectrum of t is contained in spectrum of f of t. We will show the other inclusion, namely next claim spectrum of f of t is f of spectrum of t. Let us prove the claim. So to prove this, let us take lambda outside f of spectrum of t, then f minus lambda into the constant function 1 is invertible in C of spectrum of t. C, in fact we can spectrum of t is homeomorphic with m of a. Okay, now that means this function is non-zero. F of z minus lambda into 1 is non-zero for every z in the spectrum of t. So we can define g of z as 1 by f of z minus lambda into 1. This is the inverse of f, g of z into f of z equal to 1, f of z minus lambda. The constant function 1. Now if we apply the inverse of the Gelfand map, so we will get that f of t minus lambda into identity is invertible in B of h. In fact it is in the C star algebra A. So this implies that lambda is not in the spectrum of f of t. So we have taken lambda which is not inside f of spectrum of t, and we have shown that lambda is not in the spectrum of f of t. That means the claim is proved. So with these observations we can conclude that the spectrum of f of t equal to f of the spectrum of t, which is the spectral mapping theorem for normal operators. Okay, I'll stop here. Thank you very much.